This video will cover Chapter 5 of the OCR A chemistry specification. The video is going to go through all of the points on the specification as shown on screen. The first main definition within this chapter is atomic orbitals. Now, atomic orbitals are regions around the nucleus of an atom that can hold up to 2 electrons which have opposite spins. So normally back in GCSE, you'd remember that an atom has a nucleus and then around it, it has shells, right? Now these shells contain electrons grouped up into pairs. Well, now in A levels, you need to know that these electrons are actually present within atomic orbitals. And those atomic orbitals, as you drew back in GCSE, can hold up to 2 electrons and they must be in opposite spins. Now, the two main properties of these orbitals are that they can hold 2 electrons, as said before, and they're either S, P, D, or F orbitals. Now, these are just different types of orbitals that can contain these electrons, and they're located around the nucleus of the atom. So, let's go into the two main orbitals that I need to know, which is just the S and the P orbital. First things first, the S orbital. It is drawn as just a sphere. There it is. Put this in. So the main properties of the S orbital is that within any shell, there is only one S orbital. Within any shell. And the second property is that when you increase the shell number, you increase the radii of the S orbital. Now, what is shell number? Shell number is literally just the number of shells around an atom. So if there's a nucleus here, and you have this, for instance, let's say this is hydrogen, right? And then, I don't know, whatever this would be, let's just say this is oxygen. So I'm not entirely sure, but just for the sake of argument, this is just another element. You can see that this element has a higher shell number than this because it's got 2 shells, whereas that one, the first one, has 1 shell. Now, there are 3 graphs. There are 3 graphs here that you can see when we're talking about p orbitals. The reason being, this will lead very closely within this property, so we may as well write out this property now, is that each shell contains up to 3 p orbitals. That's why there are 3 graphs here. Now, each of these 3 orbitals can have different orientations. So the first orientation is on its x-axis as such. So something like that. Second orientation would be on its z-axis as such. And then finally, it would be on its y-axis. Now, each of these orbitals can still only contain 2 electrons. So another property is that there are 2 electrons in each orbital, or p orbital to be more specific. And lastly, if you increase the shell number, you increase distance from p orbital to nucleus. So now we've said that the s orbital, there's only one s orbital in every shell. We've said that the p orbital, there's only 2. There can be a maximum within the p orbital there can be up to 3 p orbitals within a shell. However, the main distinction is that the p orbital is not located in the first shell. The first shell only contains the s orbital. Now, if you think about it, that makes more sense because the first shell for every element can only store 2 electrons. We know that from GCSE because if you're drawing an atom, you draw 2 electrons on the first shell, and then second one can contain 8 electrons. Now, the reason why this makes sense is because when you're writing out the electron configuration for an element such as this, that first shell is going to have 1 s2, meaning that this first shell, which only has an s orbital, can contain a maximum of 2, which it does have a maximum of 2. Now that you've filled out that first shell, you move on to the second shell. Then you say, second shell always starts off with S, so 2S. Now we have 8 on the outside, right? So let's say we're counting these two. So that's 2s2. Now the second shell of every element also has up to 3p orbitals, right? So that means we can do 2p. Now if each p orbital can contain 2 electrons, then in total, this has 2, this has 2, this has 2. We can have a maximum of 6 electrons within this p orbital. So if we're counting how many we actually have, we have 1, 2, 3, 4, 5, 6 remaining. So therefore, this is 2p6. Now, if there was a different element such as this, we would do the exact same process. So first shell, number 1, can only contain s orbitals, and this has 2 electrons. 2. Now we move on to the second shell. So 2 starts off with s all the time. How many does it have? 1, 2. Oh, 2. S orbital can only contain 2, so you write 2, and we move on to the p orbital. How many remaining? 1. So therefore, 1. 1s2, 2s2, 2p1. Now this will get easier as we go along more examples. The s orbital can contain up to 2 electrons. So once you write 1s2, that's it. You must move on to now the second shell. P orbital can contain up to 6. We've already said that. So once you get to 2p6, for instance, you have to move on to the third shell. The d orbital can contain up to 10 electrons. So once you get onto d10, you move on to f. And the f orbital can contain up to 14 electrons. Now, orbital filling. So you have these electrons around an atom, and these electrons must fit within these orbitals around the nucleus. There's a very strict set of rules that these electrons follow when they're fitting around the nucleus, when they're fitting into the orbital, sorry. And these are the two main ones. That orbitals fill from the lowest energy up, meaning that the s orbital always fills first. So what do I mean by the s orbital always fills it first? Well, we can show this through a diagram. Now, this diagram, you don't need to know how to fill in. This is a first year degree level diagram. However, it's just good to get an understanding as to what I mean by the s orbital fills in first. So on the side, we have energy here. And then we have the different shells. So this is n equals 1. So this is the first shell. Then n equals 2, which would be this one. Then 3, third shell. Then 4, fourth shell, and so on. So in the first shell, we know that we're only going to have one s orbital. So we can draw this, one s orbital, right? So this is an s orbital. Now, this s orbital is going to fill in with 2 electrons of opposite spins. So we draw 2 arrows there with differing spins. Then we go to the second shell. Second shell. Now, a second shell is going to contain S and P, remember that. And along the energy chain, S is always going to be below P. So there's S on the bottom and then P on the top. Reason being is because, remember, electrons always fill from the lowest energy shell. And it always fills in s orbital first, meaning that the s orbital is always going to be the lowest energy. So we fill in s, s, and then P on both, and so on and so forth. Now, there's one exception to this filling in rule where it's S, then P, then D, then F, right? So that's the general order, because you can see that as we keep going, it's going to be S here, then P here for the third shell. Now, the very specific exception is when you get to 3D. So if we're drawing this diagram out as we did for the previous shells, we can see that this is the S shell, S orbital of the third shell. Then this is the P, and then this is the D. However, the fourth shell, S orbital, lies, actually I'll do this in a different color. The fourth shell, S orbital, lies below D. So you can see here that the s orbital of the fourth shell is actually at a lower energy state than the d orbital of the third shell, meaning that when you're filling in these in these subshells with electrons, once you get to 3s2, 3p6, you actually fill in 4s2 before 3d10. So that would be the general order. Now, on a mark scheme, you actually do get the marks if these are the other way around. However, just for the sake of knowledge, it's always best to do it like this because this is specified in the mark scheme as well. Now, opposite spins. Why is it so important that these electrons have opposite spins? Or why does it even happen to begin with? Well, we know that electrons have negative charges, and negative charges repel, meaning that these opposite spins help to counteract repulsion of the negative charges of the electrons. Now, here's a very simple practice question that I want you guys to try. So, we know that chlorine by itself contains 17 electrons. However, this is a Cl- ion. This means that we'll have one extra electron. So this is going to contain a total of 18 electrons. So it's already started us off with 1s2, meaning that we've already got 2 electrons. So then we know that the next orbital to be filled will be the 2s orbital, 2s2, then 2p, and that's 2 and 2, so that's 4. 4 minus 18 is 14. So this can fill up to 6 times. So that's now 4, 6, 10. So we still have 8 electrons left over. So then we go on to 3s orbital, so 3s2. Then the 3p orbital. So now this is 12. 18 minus 12 is going to be 6. So this can fill up to 6 times, and that would be a total of 2, 4, 10, 12, 18. And that's the answer. So remember, it's always 1s, 2s, 2p, 3s, 3p. And then after this, hypothetically, if this were to be an atom with 19 electrons, then we'd go on to 4s1. Remember, this is what we just went through. We do 4s1, not 3d1. Now, this is a drawn dot and cross diagram to show the bonding in NH4+. Now, we're going to come back to this one because it's best to do this after I've covered the bonding section of this chapter. So, shorthand configuration. Now, when writing out the electron configuration, it can be very tedious once you get to the very large atoms. So there's a way to write these electron configurations in a shorthand format. Now, what this means is you use the previous, most recent halogen to dictate how the shorthand configuration is going to go. So an example is lithium. So lithium, the long format for the configuration is 1s2, 2s1. We can see that here because lithium contains 3 electrons. Now, the most recent halogen would be helium. So what we do is we write a bracket, helium, and then helium has 2 electrons. So that means this cuts out this 1s2. So all we need to do now is just write 2s1. Now, this is very irrelevant, or this is not necessary for something like lithium, but for something like potassium, where the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1, it is more relevant because now this electron configuration is very long. And just writing in the shorthand format, we can see that potassium is over here, contains 19 electrons. Argon contains 18, and that's the most recent halogen. So we can just write brackets, Ar. Now that's going to get rid of all of these because that makes up 18 electrons. And then we can just write 4s1. Now that's a very, very quick way of doing it. And the reason why is because once you get to stuff like cesium, which has 55 electrons, or barium, which has 56, then you can write the electron configuration very easily. Now, there is an important point to make about the periodic table. The periodic table is separated in terms of blocks. These blocks dictate where the highest energy electrons are in each of the subshells. So this block, the one in red, this is the S block, which also includes helium as well. That's why that's in red. But helium is just located here because it's a halogen. Then you have the D block, which is the one in blue. Then you have the P block, which is this one in yellow. And then you have the F block, which is all the ones at the bottom. Now, what do I mean by the highest energy electrons? It means that, for instance, something like argon and lithium that we just did, lithium and argon were both located on the S block. That's why you can see the final electrons are always on the S block. Now, Again, this just serves to provide more evidence as to why S comes before 3D, because you can see the S block always end in the D block, in the D subshell. However, if this followed the regular rules, then potassium would have ended on 3D1, but it doesn't. It ends on 4S1 because it's in the S block. Now, you mainly just need to know where the blocks are on the periodic table because that is assessed during the exam. Now, here we come to the bonding section of the chapter. Ionic bonding. This is the definition of ionic bonding, and it's been the same since GCSE, so you should know this fairly well anyways. It's the electrostatic attraction between positive and negative ions. That's it. Holds together cations and anions in ionic compounds. That's not necessary for the mark. The main point is that it's an electrostatic attraction between positive and negative ions. Now, dot and cross diagrams. Again, this is very simple because it's been the same since GCSE, so you can just write potassium here, which is the positive ion. Fluorine there, which is the negative ion. And it's negative because it takes that one electron. The same for magnesium chloride. I'll give you guys a chance to do it yourself. So that's 2 chloride ions, where it takes 1 electron each, and then 1 magnesium ion that gave away both of its electrons. Alternatively, you could just write out 2 chloride ions, but I find that a bit tedious. Now, the structure is a giant ionic lattice structure, again, the same since GCSE, and if you were to ask to draw it out, it would just be something like this, where it's just a regular arrangement of ions. Now, properties. So for melting and boiling points, it's a solid at room temperature because, and this is a very important point, there's not sufficient energy to overcome electrostatic attraction forces between the oppositely charged ions. Therefore, there is a high melting point and boiling point. Now, solubility, they're always very soluble because they're polar. Now, conductivity, in terms of electricity, as a solid, and this is extremely important terminology because these are all the marking points, as a solid, the ions are fixed in place, of course, meaning there's no mobile charge carriers, meaning that it is non-conductive as a solid. As a liquid, the ionic lattice is broken, which means they're free to move charge carriers, making it a conductor. Now, the summary is just high melting and boiling points, highly soluble as a liquid, highly soluble and conductive as a liquid, but not as a solid. Now, covalent bonding, important definition, strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. That's a very important point. Normally, this goes for 2 marks, and that's the second mark, but if it's a 1 mark definition, then you have to include this point for the mark. It occurs between non-metal elements and polyatomic ions, such as ammonium. So an important point for covalent bonds is that the bonds are localized. What does this mean? This means that they only act between 2 atoms. Now, this is a difference between ionic and covalent bonding. So there are many types of covalent bonding, the first one being single covalent bonds. This is a very simple concept because it's the same as in GCSEs. You can just have, for instance, a very simple example, 2 hydrogen atoms that share a pair of electrons, or that share electrons, where the displayed formula is just this. Another good example is water, oxygen, hydrogen, now, there's a very important exception when it comes to just regular covalent bonds. So as you can see in this example of water, this follows the octet rule. Now, this rule says that for a covalent bond to form, the atom or the central atom has to form that covalent bond for 8 outer electrons. 8 outer electrons being the most stable form of that atom. However, there's one main exception to this rule, and the main exception is boron. Now, boron does not follow the octet rule, meaning that boron only forms 6 outer electrons. So an example of this is boron trifluoride. Now, you can see the total number of electrons are 6. This doesn't follow the octet rule, so it doesn't need an extra set of atoms to form 8 outer electrons. It's perfectly fine and perfectly stable with 6 outer electrons. Now, there are some other examples. Now, the reasoning as to why all of these elements can do this is because they can hold up to 18 electrons in their outer shell. So an example is, or as a diagram, this would be represented such as, if you were doing sulfur difluoride, which is SF2, then that would just simply be, just as a really quick example, or with the 6 fluorines, the sulfur can form a complex such as, now of course this is a very rough example because I'm not drawing all of the electrons, I just want to show this as an example to show how many electrons the sulfur itself can hold, not the fluorine. So you can see there's 2, 4, 6, 8, 10, 12. So there's 12 electrons there. But the sulfur atom is completely fine and stable in that state, so that's why it can form this. However, the main example that you must be aware of is boron. Now, the second type of covalent bonds is just multiple covalent bonds. So double bonds, but just as a quick example, double bond O, and triple bonds as well. So something like, it's going to be between 2 carbons, making alkyne, something like that. And then lastly, you have dative / coordinate covalent bonds. Now this is a covalent bond where the electrons are supplied, or the shared electrons, I should say, are supplied by only one of the two bonded atoms. Again, a good example of this is ammonium, NH4. Now, when drawing out the dot and cross diagram, it would be N, H, 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 H. Now, all of these electrons are shared. However, to this hydrogen, only the nitrogen is providing those 2 electrons. So you can see where there's a dot here, there's a dot here and a dot here and a dot here, it shows those electrons are also being supplied by the hydrogen. However, in this instance, there's only 2 crosses, meaning that the nitrogen is the one that's providing all of those electrons for that hydrogen to still be able to bond to it. Now, this isn't done. We, of course, need to add the brackets because it is positively charged, and that's it. Now, if you were to write this in a displayed formula, it would have to be after the H's here as a regular displayed formula. However, for this bond, to show that the electrons are only being supplied by the nitrogen, we draw an arrow from the atom that's doing the supplying to the atom that's taking those electrons. This arrow shows, very simply, that that nitrogen is the one that's giving all of the electrons. It's a very simple concept. And then you just add the brackets and the plus. So going back to this question, the answer is simply the exact same diagram that we drew in the last example. And that is it for OCR A Chemistry Chapter 5, Electrons and Bonding. I hope this video helped, and I hope you have fun revising.